So in the last video, this is where I left off. And it was this idea that we had a Kekulé structure as well as a condensed structure as well as a Lewis dot structure. Why are there so many different options? Why is there so many things for me to choose from on how I want to draw these molecules and the structures of these molecules? Well, here's kind of my honest answer. All right. What you have been doing up to this point has been something that we call the Lewis dot. And that Lewis dot structure includes the dots that might be present on the structure. Well, there was a certain point in time where someone is going to look at what we've been doing all of this time and take example carbon tetrachloride, right? It was these 4 chlorines around carbon, and look at all of the dots and the time that I have to waste in order to get there. I mean, goodness gracious, people, who wants to take the time to draw all of the dots one by one when there's 24 of them in this case, just to kind of convey the proper structure of carbon tetrachloride? So the Kekulé structure kind of came next. I'm going to rank this as number 2. And someone said, I think I'm too lazy to draw all of these dots. So why are we drawing the dots? If we all know what these structures are supposed to be, and we are versed in the chemistry field and in the laboratory sciences, then we should know that those dots are actually there to begin with. Why do I want to take the time, and why do I want to take the trouble to draw all of them? So a Kekulé structure was invented, and the Kekulé structure said, listen folks, we're going to draw these structures like you have been doing, but we're going to leave off the dots. There's going to be no dots that we are going to draw. You assume and you understand that those dots are there. So looking at this structure, I'm going to see the structure, and if it's a Kekulé structure, I know that those dots are going to be present even though they are not drawn. This is somewhat like a shortcut method. That's why this was kind of developed back in the day, and that's why this was one of the options. Well, a little bit later down the road, someone's going to come around and wise up and say, well, you know what? Lewis dot structures, it's a lot of trouble. You got to draw all those dots. That's not fun. Nobody wants to do that, right? We want to kind of get to the point. And then the Kekulé structure made a step in the right direction, but at the same time, there's chances that I don't need the actual full-blown structure. I don't need to know that chlorine is actually attached to carbon in that way. So the condensed structure actually includes no dots, and it also includes no bonds for the most part. Okay, so basically what that means is that this structure will turn into carbon in the center and 4 chlorines that surround it. And I know, because I've been trained in how I draw these structures and how to visualize these structures, that molecule is oriented to the direction of the left in a tetrahedral fashion. I don't need dots in order to make my determination. I don't need bonds in order to make my determination, but that is the purpose of the condensed structure. All right. So if you look at an image from your textbook, you're probably going to see something similar to this, and it compares the Kekulé structure to the condensed structure. So keep in mind, they're not even really focused on Lewis dot in this image because Lewis dot includes the electron dots. That's why it's called Lewis dot. All right, so Kekulé structure is going to take the Lewis dot structure, and it's just going to get rid of the dots that are going to be present. Look, hydrogen has 2, hydrogen has 2, hydrogen has 2. This carbon in the center, 2, 4, 6, 8. And you're probably looking at this, and you're probably saying, whoa, wait a minute, we've not done anything this complicated. No, we've not. We're going to build up to this, and I'm not going to probably ask you this on a test, but you've got to start getting used to seeing these types of structures because these are very common in organic. In a Lewis dot structure, this bromine has 2 from that bond, So it would be understood that there are 6 dots around that bromine in order to make it an octet. However, in the Kekulé structure, we do not write those 6 dots. We leave them off because we know that other people know that they're supposed to be there. This hydrogen on top is okay too. The carbon, 2, 4, 6, 8. This hydrogen at the bottom, 2. That's good. Next carbon over, 2, 4, 6, 8. The hydrogen on top has 2. The hydrogen on the bottom has 2. Next carbon over, 2, 4, 6, 8. So that carbon's good. The hydrogen on top is good. It's got 2. And the chlorine down below, well, it's actually has 6 dots around it. The Lewis dot symbol would have showed you those 6 dots. The Kekulé structure, though, does not. So we erase those dots around it, and we clean up the structure a little bit, and we save you a little bit of work. Now, over here to the side, you are going to see, hold on, let me get rid of this aggravating header. Over here to the right-hand side, you are going to see the condensed structures. So they're giving you 2 options here. There's 2 different ways that you can draw these. I actually prefer this way over here to the right, and I'll tell you why in just a second. But what they've done is that they've gotten rid of all the dots and all of the bonds. They don't draw those either. So they start off with this carbon, which is what we call part of the main chain, right? So here's that carbon, there's the C. And then all of the hydrogens that are attached to that carbon are written next. So that's why you see the CH3. That's the option there. All right. Next carbon over, we see the next one here. So this would be the next one there. And then we have a hydrogen attached to that carbon. And we also have a bromine attached to that carbon. So they just go ahead and draw it out just like that. H and Br. Then we go on to the next carbon. All right. So the next carbon in line is here. And we have a hydrogen on top and a hydrogen on the bottom. So here is that next carbon that they've written into the structure, and we have a hydrogen on top and a hydrogen on the bottom. So there's 2 hydrogens. So I write H2 that's there. You know, writing CHH is a little weird, and it looks funny. So we condense it a little bit. It's called the condensed structure, right? So I write CH2 there. The next carbon over, well, same kind of story there, folks. We see the next carbon. Up above, we see a hydrogen. Down below, we see a hydrogen. So here is that particular carbon, and there's 2 hydrogens on that carbon, so we write a CH2. Finally, the next one, not finally, but almost finally, the next one is another carbon, and we have a hydrogen attached to it, and a chlorine that's attached to it as well. So here is that next carbon. It's right there. There's a hydrogen on top, and a chlorine that sits down below. And then finally, that last carbon, I'm going to leave black. So that is a carbon with 3 hydrogens. So therefore, it is a CH3. So that is the way that we draw a condensed structure here in order to remove all of the bonds and in order to remove all of the dots that we know are supposed to be there. We have a trained eye, so we need to start getting used to those condensed structures because we're going to be using those all the time. Now, I told you there was a choice, right? It says or. And I told you that I really like the version over here to the right-hand side, and here's the reason. Carbons and hydrogens are very common. There's nothing special about them. I'm sorry, but there's nothing special about them. So those carbons and those hydrogens, if you read across the line, are all included on the same line, right? CH3, CH, CH2, CH2, CH, and CH3. What we've done here, though, is that we have singled out this bromine because it was kind of different. And maybe we want to give it priority. We want to put a focus on it because that could be very important later down the road. So instead of sandwiching that bromine into that main chain and just writing it straight across like this version over here to the left did, then we can draw a line and we can write bromine there just to give it a little priority and to single it out a little bit more. And this is going to become important much later down the road, but this is the way that I like to see the condensed structures. Anything that is not carbon or hydrogen typically gets a bond and it pokes out of what we would call the main chain. There's also some times where we might not get a hydrogen here, but we might actually have another carbon there as well. So take a look at this example down here at the bottom, okay, or toward the bottom. We have CH3, CH2, CH, and this is not a traditional hydrogen that's there, right? This is a whole grouping of another CH3 group. So I could write it in the condensed structure form, and you're seeing that right here. So carbon first one, second carbon, third carbon in, I have the hydrogen that's pointed out to the top, and then this parentheses means that this group is pointed or attached onto that particular carbon. That is why it's written that way. That way, you know, when you look at this condensed structure, that it's not part of the main line that goes straight across. Okay, so this carbon and this hydrogen and this CH3 group, because it's in parentheses, all belongs to this part of the molecule right there. All of them are in green. All right, well, if I scan through the condensed structure, I'm also going to see an OH in parentheses. That OH means it's not part of the main chain, right? We don't really have issues with hydrogens, but all of these other weird, funny groups, we like to single those out when we can. So that parentheses means it's attached onto the previous carbon that was drawn in the main line. And you're seeing that here. Here is that particular carbon, there is the hydrogen on that carbon, and here is the OH on that carbon. And here is that same carbon in the condensed structure. There's the hydrogen attached to that carbon on the condensed structure, and this OH group is attached to that carbon. So that is what the parentheses mean in condensed structure notation. It means it's an attachment, and that attachment is attached to the previous carbon that came prior to drawing those parentheses. Well, those parentheses, again, I think are very problematic for people. I don't like to see them. I don't like to look at them. So I prefer the version to the right-hand side. And they basically take the structure, the Kekulé structure, CH3, CH2, CH, but because this was a little different and because it was a little special, it was hanging out of the main line as we go across, that CH3 we continue to put on that spot, and that way I can single it out and I can say, listen, this might be important a little bit later, okay? The same way with the next to the last carbon, I see a CH, so I see the CH drawn condensed here, but I still poke out the OH and I push it down. I could push it up if I wanted to at this point, it doesn't really matter, but I normally try to match the Kekulé structure when I can. So that OH is singled out, that OH has a preference on it, and I know that that particular group might be a little bit important later on down the road, okay? So this is how we do condensed structures and Kekulé structures. In the condensed form, it's also okay to do something like this. All right. So what they've done is that they've showed you, hey, we have a CH3 group that's here, and we have a CH3 group that's here. Well, if you look at all of the other carbons that's in the middle, they're all the same, right? It's CH2, 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 CH2. They're all the same. So they shortcut that as well, and they put a parentheses here, and that parentheses, they put CH2, and they put a 4 after it. And now you're going to say, well, wait a minute, I thought you told me the parentheses meant that it's attached to this particular carbon that comes immediately beforehand. Well, if you take a look at the Lewis structure, there's no way that that could be possible. So this is the problem with parentheses. And this is one of the reasons that I do not like doing this form. I like to keep it consistent. So if you do the right-hand versions every single time, what you'll see is that you will not be confused with the parentheses. The groups that would have been in parentheses are actually attached to where they need to go. It's as simple as that. So two versions of condensed. You pick out which one you like the best. I prefer the ones over on the right-hand side of these examples and not the ones in the middle, okay? So that's the story with condensed structure and Kekulé structure and why we have them. There's also another shortcut that came into existence as well. A lot of people had problems with polarity. So notice that we drew this arrow, and the arrow pointed to the negative side of the house, and this was really the positive side of the molecule. Well, a lot of people thought that drawing these arrows every single time was a little bit of waste of time. So they wanted to come out with a shortcut for polarity as well. And this is only one way that we can represent polarity, or what we can represent as a dipole. Remember, we said both of those terms are interchangeably used. Well, if I go back to the HCl, that very first example that I gave you, I'm going to redraw the Lewis structure here. There we go. And we can also assign polarity a different way. If I can figure out where the negative area of the molecule is at, and that's here, where all of the dots are at chlorine, what I do is I do a little d that's a squiggly d, and then I draw a minus right up above it. What this means is a partial charge, and that charge in this case is a negative. So it's not full negative, but it's partially negative. That's how we would represent that. Well, if we can do it on the negative side, we can also do it on the positive side as well. So I can write the little squiggle positive there, and that squiggle positive basically means that this is a positive area of the molecule. So it saves me from drawing the arrows, trying to figure out which way I need to point it, which way I need to end it up. We also did oxygen or water with the oxygen here, and we said that oxygen was bent and it had two pairs of electrons. So there's the structure for H2O. We can do the same thing here. This one is slightly positive, this one is slightly positive, and this one up here, it's slightly negative because that's where my electrons are going to be. No big deal, right? Another example that we did was ammonia. So we had nitrogen with 3 hydrogens on it, and there was a free pair of dots on that nitrogen. So if you don't want to draw the arrow and you want another shortcut, I guess is why we're talking about this, then you would do squiggle positive, squiggle positive, squiggle positive, and squiggle negative. That's as simple as it is, folks. That's all there is to it. So it's just another way to represent charges, polarities, dipoles, however you want to call it. That's basically what it's referring to, okay? Finally, something else that I want to say before I stop this video, because we're still talking a little bit about review and recap and shorthanded methods. Because we are talking about polarity or dipole numbers, here's a table that they provide you in a textbook, and it just basically represents different types of bonds that you might see and how we rank them. So if you look at what's common here in the very first column, right here's what we're going to be looking at, you see all of the hydrogens that are all the way down, and you see the hydrogens attached to a carbon, and then a nitrogen, then an oxygen, then a fluorine, then a chlorine, then a bromine, then an iodine. I told you that the fluorine is the most electronegative, right? So fluorine is the most electronegative of all the atoms. And look at the dipole moment here. That dipole moment is 1.7. It is the highest that's in that particular column. And the reason is because fluorine is very electron greedy. That's what electronegativity means. So if he's electron greedy, then he's going to hoard up all of the electrons on his side whenever he can, and that's where they're going to hang out. So he's being true to his definition. Well, if he's hoarding up all of the electrons over here, then that means that this polarity is a little bit greater. And we can measure that polarity. We have a term that we use. It's called dipole moment, and that's abbreviated with a D, and that dipole moment of that bond is a 1.7. Well, oxygen is less electronegative. So he's less electron greedy. And because of that, he still hoards up the negatives over here, just not as much as fluorine does. So we still see polarity, we still see a dipole moment, but it's a little bit lower, and we see 1.5 now compared to 1.7. And the reason, it's an electronegativity driven value. Okay, carbon to hydrogen, look at here. This carbon to hydrogen bond, this has a very low dipole moment. This dipole moment is a 0.4. So it's almost close to zero. So what that means is that carbon's electronegativity and hydrogen's electronegativity, it's almost the same. It's not identical. If it was identical, then it would be a 0. But it's almost the same. I think the values for electronegativity here are maybe like 2.4 and 2.1 or something similar to that. Well, what does that mean? Well, that means that carbon and hydrogen is really close to being nonpolar. There is not a tug of war that happens here, people. Carbon and hydrogen, when they form a bond, one of them is just a little bit greedier than the other one, but for the most part, they're kind of playing the same ball game here. So one of them is never going to really truly outdo the other one. They'll get close, but it's nowhere near anything like the one that nitrogen has, or oxygen has, or fluorine has, or chlorine has. I mean, we really have to go down here and look at iodine in order for that to kind of become a 0.4 again. So the moral of the story here is that the higher electronegativity value and the higher the electronegativity difference is, the higher the dipole moment is going to be. In other words, the more polar that bond is going to become. This is good news, though, because most of our organic structures are CH bonds, and that CH bond is close to 0. Therefore, it's close to being nonpolar. Therefore, these atoms are never in competition with each other. Only when we begin to add other things. So that carbon and hydrogen is a pretty much even type of bond. The same story happens over here to the side, or to the right-hand side. You see this carbon's being consistent, and what they're doing is that they're changing the second one all over again. Once more, fluorine is the most electronegative, it's the most electron greedy, it's the most polar because that's where the electrons are going to stay most of the time, and you're seeing the highest dipole moment for that particular bond as well. If you go to the carbon-carbon bond, of course they're the same. This is a staple of organic chemistry, and that carbon-carbon bond has a dipole moment of 0. It is truly nonpolar. It is not in competition with each other, and when those two things hook together, they are not trying to outdo each other. Again, that is very good for organic, because that leads me to believe that these things might be a little stable. There's also another way that we can represent polarity, and this is what we call an electrostatic potential map. All right, so an electrostatic potential map is just a fancy word that describes a computerized model of polarity, since that's what we're talking about right now. And they use a shade of colors. Those colors go from red to blue. And red, of course, we always think of negative when we look at reds. And blues, we think, hey, those are probably positives. And that's exactly what these colors represent. So here's an electrostatic potential map of a molecule, or a couple of different molecules. And if you look at the middle one, this H2 is H and H, and that's all you get right there. Okay, hydrogen has 2, this other hydrogen has 2, there's no free pairs, there's no dots anywhere. This is a very non-polar molecule, and we're actually seeing that in the electrostatic potential map. This is all green, and that green means that it's a very neutral area. The LIH over here to the side, all right, well, by looking at the potential map, it looks like the hydrogen this time is our negative area, and that's where the electrons are going to be located. And then it looks like our lithium on this side is going to be a blue area, so this would be more of a positive area for that particular molecule. HF would be the same way. This hydrogen would be positive, and the fluorine is on this side, so therefore that would be negative. They try to match the electropotential map up to the way that we've drawn the structure down here below. So H is to the left and F is to the right. Okay, Li is to the left and H is to the right here. Here's another version. This actually shows you a little bit of the molecule in the center, and then they cover up that molecule with colors. And those colors, again, are going to be the same. Red areas are going to be negatives. Blue areas are going to be positives. Here's H3O plus. Look at here, folks. There's a positive there. So as you can expect, the majority of that molecule is blue, which is a positive area. Here's water, H2O in the center. That water, we know that there's free pairs of electrons here. We've done that structure over and over. This is a negative area of the molecule, and you can see the reddish peak that's right here in the electrostatic potential map. The rest of the structure is bluish, and the rest of this structure is going to be a positive area. Here's the OH group. This OH group, it's not uncommon to see that negative there, so therefore it's no surprise that the majority of this molecule is reddish in color because it does carry a negative charge that's assigned to it. So that's really all that you have to do, people. If I give you an electrostatic potential map and you see some colors, it's going to say, all right, where's the negative area, where's the positive area, and that's about it. So this is where we're going to stop. In the next video, we'll pick up from here. We'll keep talking about structures. We'll keep talking about how to represent these things, and we'll bleed into a little bit of the organic at the same time. And if you've been paying attention, we've kind of already done it, because I think that some of this stuff was probably new to you at this point. So, if so, that's good news. You're at least learning something in the first module, and as long as you're learning, I'm happy.